Hey guys, welcome back to the old mill shed. Today, we're going to geek out a little bit on applied thermodynamics. This is one of my favorite subjects. Ever since I had my first thermodynamics class, I've always loved it. And I have a issue here that I need to use this to solve. So a quick backstory. I rebuilt the engine on this tractor about 2-3 years ago. And I looked at the radiator. The radiator was put on somewhere around 1984. It is a copper radiator. I flushed it. It didn't seem to be in that bad a shape. But whenever we're getting up around 100 degrees, which is a big part of the summer here where I live, the machine, anytime it gets under a little bit of load, will want to overheat. Now if I'm just puttering around, like pulling my a wagon that's got like my tools in it, and I'm just like moving from one job to the other, and I'm just using it to haul my tools around that I'm using throughout the day, it does fine. But if I put like a bush hog on it, or if I need to pull a hay rake or anything like that, if I get up around 100 degrees, it starts overheating on me. If you recall the last video, when I put the new radiator on the 4540, I gave y'all a little short formula on how to size a radiator. Now that was a very quick and dirty kind of shortcut formula to give you just a baseline to work from. It really didn't go in depth to what all the factors go into it, and the formula I'm going to give you today addresses those shortcomings. And here is your formula. Now we're going to go over each individual part of it, but the overview is the area of radiator required in square inches equals your horsepower multiplied by your fuel type coefficient, your air induction coefficient, your application coefficient, times your base heat rejection coefficient, divided by your radiator material coefficient, multiplied by how many cores you have. That's also a coefficient. So 3 cores isn't going to equal 3. Your airflow coefficient multiplied by your delta T, which is the coolant target temperature minus your ambient temperature, and that's in Fahrenheit. First things first, we're going to go through each one of the components, each one of the coefficients for each part. We're just going to walk through and explain what they are and what the values are. And then at the end of this, I have some real life data put into a spreadsheet of the actual problem I'm facing, as well as several different proposed remedies to that problem, and which one or combination of remedies will give me the best result. So our first coefficient is a fuel type coefficient. Different fuels burn at different rates and put different amounts of thermal energy into the engine block and the coolant. So we set gasoline at 1. Propane puts a little more energy into the coolant. So the coefficient, if you're running propane, is 1.05. If you're running a 4-stroke diesel, typically when you're talking thermodynamics and you're talking about an internal combustion engine, a third of your energy goes into the engine block and the coolant, a third goes into the exhaust, and a third is turned into mechanical power. On a diesel engine, a little bit more of that thermal energy goes into the exhaust, and a little bit less is rejected into the engine block and the coolant. So you use a coefficient of 0.85. Now, for you guys who are super awesome and run two-stroke Jimmys, first of all, I'm jealous of you. They're one of my favorite engine series. But you are firing on every stroke, so you don't have that exhaust stroke that a four-stroke diesel engine has. So your coefficient is going to be 1.2. Next up is our air induction coefficient. So if you're naturally aspirated, the engine is pulling its own air in, your coefficient is 1.00. If you're turbocharged, your coefficient is 1.15. And if you are supercharged or blown, this is where you guys running those two strokes really start taking a beating in this equation. Not only do you have a higher fuel type coefficient, but you also have a 1.25 air induction coefficient that you're having to deal with. Next up is our application coefficient. Daily driving, you're just riding back and forth to work. You're not doing anything special. Your coefficient's 1.00. Performance driving, if you're a little bit more aggressive, you're in the throttle a little bit more, that's 1.15. Light tillage, this is going to be something like running cultivators, maybe a bush hog, maybe you're on, maybe you got a flat belt on your tractor and you're pulling like a small thresher or a little grist mill or something. That's going to be 1.25. Hauling and towing, self-explanatory, 1.3. Heavy tillage, that's when you got the plow in the ground, you got a big disc you're pulling, maybe a middle buster, something where you're getting down and that engine is under load constantly, is 1.4. Competition, that's when say you're down here at VIR and you're just running flat out, hard as you can push your vehicle. That's 1.5. And then the killer is stationary, because the fan is doing all of the work. That's going to be 1.6. Now, one thing about a farm tractor, some things that we hook up to, we might be doing light tillage, we might be doing heavy tillage, or we may have it on a belt, and we've got it maxed out what it can do on a belt. So you always want to design your radiator or your cooling system, or your cooling setup, I should say, to the highest coefficient that you're going to have. For instance, my TO30, the highest coefficient it's going to have is going to be heavy tillage. Now my 4540, I do have some stationary equipment that I run with it under significant load. I have it set up on the 1.6. Next up is our radiator material coefficient. Aluminum transfers the heat the best. It gets a coefficient of 1.00. Copper comes in next at 0.88. We will see a little bit later on how much this helps us. And then if you've got an old machine, you may have a full brass radiator. The coefficient on that is going to be 0.82. Some of y'all probably looking at some charts right now going, now hold on. Copper is highly conductive to thermal energy. And you're right. Back up. While pure copper is highly conductive, traditional copper and brass radiators use thick solder in smaller tubes, making the aluminum radiators much more efficient per square inch. Next up is our cores or rows coefficient. Now the way a radiator is made, typical on a tractor, your tubes are vertical and your fins are horizontal. If you've got 2 rows of tubes, your coefficient is 1.0. If you have 3 rows of tubes, you're at 1.3. And if you have 4 rows of tubes, you're at 1.5. And here's the second issue with you, well, not with you two-stroke guys, that sounds horrible. Here's the second issue for you two-stroke guys. Two-stroke diesels usually run a lot higher amount of volume being circulated through the block to help keep it cool because of the increased combustion temperatures. So you may be flowing twice as much water through your block as a 4-stroke guy in a similarly sized engine. This is not going to change the required surface area of your radiator. However, you are going to have to make sure you have bigger cores, bigger diameter pipes going through your radiator, so you don't build up back pressure and blow out usually the thermostat housing. If you're flowing at twice as much volume, circulating twice as much volume per minute as what that radiator is designed to handle, your pressure is going to build up between that thermostat housing and where it goes into the radiator. If you're lucky, you'll just blow out the hose. If you're unlucky, you're going to crack your thermostat housing, or you're going to blow out something much more expensive. A couple of things when it comes to the radiators, especially when you're starting to talk about a 4-core radiator. The more cores you have, the thicker your radiator is, and lots of times a standard fan will struggle to pull the air through 4 rows of cores. In that situation, lots of times, if you want to run a standard fan, a 3-core is actually going to be more efficient than a 4-core, because you're not slowing that air down. It can actually pull through. If I run a 4-core radiator, typically, not all the time, typically, I will put on a high volume electric fan to make sure that I am pulling the airflow at a sufficient rate to actually use the extra capacity of that radiator. The next coefficient we're going to look at is V sub A, your airflow coefficient. Excellent airflow, your high speed ram air, a lot of air coming through your radiator or through your grill of your car. High CFM dual electric fans on a full shroud. That's excellent. Good is like a standard highway speed, standard clutch fan, and a full shroud. Fair, low speed operation like off-road, standard fan, no shroud. You know, even at low speed, and I did have a shroud, I would still keep the 0.6. It's not really going to change that much. Poor is stationary or agricultural equipment, and you're basically relying on the mechanical fan at this point. Now, in my situation, I have a 4-blade fan, and it's fully shrouded. Definitely poor. I can bump up to, say, a 6-blade fan. Instead of having 0.3, I'm actually going to be probably closer to 0.6, just because of how much more CFMs it pulls through. In that case, I might not go to full 0.6. I would go to like 0.45, maybe 0.5 with that setup. We're almost done, I promise. Delta T, this is your temperature delta, and it is your target coolant temperature minus your ambient temperature. So say you are targeting 150 degrees coolant temperature, and say it's outside, say it's 100 degrees. Okay, let's say it's 95 degrees outside. But under the hood of the tractor where that radiator sits, let's say it's 105 degrees. So you would use the 105 degrees because that's where the radiator is sitting. You know, you've got engine heat coming back, or maybe the sun's really bright and the shrouding or the hood on the tractor is a dark color, it's heating up. So you want to use the higher temperature where the radiator is actually sitting. The last one is the base heat rejection constant. And this is just a factor derived from real-world testing and historical data rather than purely theoretical physics. It's based on the 1/3 thermodynamics rule, 1/3 mechanical power, 1/3 to exhaust heat, and 1/3 to coolant. This makes everything work. It allows us to use simple numbers for all the other inputs to get the answer that we can actually use. So now that we have the formula and we have broken down each input, let's look at a real-world analysis of my TO30. I tell you what I'm experiencing, and then we can look at the numbers, and the numbers actually back up what I have been seeing. Okay, so here is the current situation on my TO30. 30 horsepower input, and actually I'm closer to 35, but we're just going to go with 30. Fuel type is gasoline, so my input is 1. Naturally aspirated, my input is 1. Light tillage, 1.25. My radiator material is copper, so my input is 0.88. I have 3-core radiator, so my input is 1.3. My airflow is agricultural, low speed, so my input is 0.3. My temperature delta is 50. My target coolant temperature is 150 degrees, and I have under the hood at 100 degrees. Of course, my base heat rejection is 120. So that gives me an input total of 4,500. That's the top number. And then it's divided by the heat dissipation capacity per square inch, which comes out to 17.16. This is, we need a radiator size of 262.238 inches. My radiator size is 17.25 by 15.25, which is 263. So at 100 degrees Fahrenheit at the radiator, I am at my limit. And that is what I'm seeing. If I stay in the light tillage mode and I'm right at 100 degrees, it will come up to 150 degrees and it will stay there. If I start pulling a big hill, get into a thick patch of grass to where it's pulling just a little bit harder, or I'm out on the top of the hill where it's just a little bit warmer, my temperature gauge will start to climb. It will go up to about 160, but it won't go any further. It will not go into the red, but it will run about 10 degrees hotter than where I want it to. Now that we know the current situation, let's look at some things that we can change and see how it changes the output from the formula, and see if we can't select the best route forward to fix this issue. So the first way we can try to remedy this situation is the cheapest and probably the easiest, if not the most practical. I can cap operation at 90 degrees Fahrenheit. That gives me a temperature delta of 60 instead of 50. And it drops the required radiator size from 263 down to 218. which gives me a safety factor of 1.2. Now that will work. And I know this will work. If I was to go outside right now, it's 86 degrees outside. I was to put the bush hog on, I could run around here all day long. It's going to come up to 150 degrees where the thermostat controls it, and it's not going to come above it. The only problem with that is, if I cap it at 90 degrees, I can't use this tractor the biggest part of the summer. The second thing I can do is I can swap out for a 3-core aluminum radiator. This is a $125 part. I can put my temperature delta all the way down to 45. So I can set it to where I'm outside up to 105 degrees. That's going to give me a required radiator size of 256 against a 263 actual radiator size. So that will work, but I'm at my limit at 105 degrees. Okay, the last scenario is we add the aluminum radiator, which I'm going to have to replace the radiator on that machine within a year or two. In a way, it's already starting to leak. It's been on there for about 40 years. An aluminum radiator is half the cost of a copper radiator, $120 as opposed to $238. So there's a cost savings there as well. If I add the 6-blade fan, which flows about twice the airflow, which that is going to put a little bit more pull on the engine. So if that ends up being detrimental, we can always change over to an electric fan fairly cheaply. But that drops the radiator size required to 128 inches. That radiator is 263. That is twice the cooling capacity that I would need with that aluminum radiator. And a whole retrofit would be less than $200. This is probably what I'm going to do. Hey guys, so that's pretty much sizing the radiator in a nutshell, and how you can use the formula to change little things to see what's going to be the most efficient way to fix whatever issue you're having. And when I'm doing these, I always want to give myself a little bit of wiggle room. So I like to go at least half again bigger than what I require using this formula because it's so much more accurate than the old one where I would try to go 3, 4, 5 times bigger. And I always want to give myself a way to upgrade it more, hopefully cheaply. So I'm going to a 6-blade fan, which should work with the aluminum radiator, and I'd be fine. But say if I needed a little bit more, well then I could cheaply just take the 6-blade fan off, sell it on eBay, get most of my money back, and put an electric fan on, which would definitely get me up to much more cooling capacity and keep me well within operating temperatures. So that's the video. I hope you enjoyed it. I hope you found it helpful. If you did, give me a thumbs up. Subscribe and hit that notification bell. It helps the algorithm a lot. We'll see you here next time under the shed.